Welcome back to another episode of Learning by Doing OpenFOAM. First and foremost, I want to say Happy New Year. Or actually, I should say Happy Persian New Year or Happy Nowruz. It was actually the first day of spring, so it was a couple of days ago on 20th of March. But I think it's not that too late to say Happy New Year. And I hope that this year is going to be sort of a prosperous one with health and hopefully a little bit of peace in the world as well, because we are in such a chaotic and turbulent sort of world conditions right now. Anyways, today we are going to talk about interesting topics, and namely, we are going to talk about equations of a state and how we can write our own equations of a state in OpenFOAM. In a nutshell, I would summarize it as this: writing your own equation of a state is not probably that straightforward. And the reason for that is the way that OpenFOAM basically bundles everything into those thermo packages. So those equations of a state are not actually a standalone entity or whatsoever you want to call them, so that like you compile them and then you basically can use them in any scenario or simulation that you want to have. It's a little bit complicated and messier than that. But don't worry if you don't understand what I mean by now, because once we deal with the code, then you basically understand everything that what do I mean by these sentences in the beginning. Again, like the previous episode, this episode is also inspired by a question which was sent on CFD online. So let's take a look at it. On 17th of January, Diego Bindoni, apologies if I'm pronouncing that wrong, he basically wrote, "Good morning, I'm performing an alias simulation of a round jet in seawater using OpenFOAM 12, and I would like to change the equation of a state from the default one to the actual one for the seawater, which depends on temperature and pressure, and it also it's a lot complicated and long." And he adds, "Do you know how I can code this, or do you have any template or similar examples that I can learn from? And thanks in advance for the help, and let me know if I can provide further information." And then on 7th of March 2025, a user called Aaron comes along and says, "It's easy. Here's the equation of state models. In OpenFOAM, source them physical models, species, equation of state. All you need to do is to create a directory in there and add your own equation of state. And after that, you need to define your new equation of a state in a few other places so that the compiler recognizes it." Okay, so this is a perfectly fine answer to this question. But the problem is, once you're sort of a beginner where you start with OpenFOAM, or you're learning basically at the learning phase, then writing your own equation of state is like quite challenging enough for you, let alone if you want to figure out that at what other few places that you need to add those equation of state, and what do you mean by compiler like recognizing it. So I was just thinking that we can probably like provide a possible solution or a sort of a detailed guide how you can write your own equation of state. And by the way, I want to add two things in here. The first point is that we don't care about the specifics that Diego mentioned. So we are going to sort of give a general answer so that everybody can benefit from that. And if you understand the logic, then probably you can also extend it to your own work. And the second thing is that, as I said, this brevity that you see here is not probably enough for somebody who is just beginning to use OpenFOAM, or who is just beginning to write some stuff, like some pieces and bits of code to perform like very specific simulations. So we're going to add some information on top of that. So we do have a perfectly fine, and we have a starting point as well. We know that these equations of a state are located probably here, and we want to verify that. So let's just jump into the code. You see that I have two terminals open here. The only reason that I have two is because sometimes I need to check some stuff and show you some things very fast in the background. That's why I have that one. Both of them are fired with OpenFOAM v2406. And that's it. So let's jump into the source in that location that he said, in thermophysical models and species, I think, and equation of state. Yeah. So we do verify that all the equations of state are basically defined in here. Let's take a look at one like perfect gas, probably the simplest one, that H. You see that the description says perfect gas equation of state, and then you can see that it's like a templated class, template parameter of species, and it also publicly inherits from species. And you can take a look at how this class is basically defined. It's basically fine. So at the end of the day, we wanted to write our own equation of state, right? So let's just copy this. This sounds very fine to me. So I'm going to my run directory. I'm going to make an EOS directory or equation of state. And I'm going to also make two other directories. Right now it's empty. I'm going to make source code, and another directory called test case, because we also need to test our equation of state, right? So let's go to source code and copy that perfect gas in here. So we need to generate a new equation of state, but we're not going to write that from scratch. We're just going to pretend that we have written this one on our own. So let's just move this perfect gas to custom perfect gas. Maybe just, I don't know, a stupid name, but it works. So now let's change everything in here. Like .c should be custom perfect gas.c, and let's do the same for .h. Yep. And finally, we have this one, which we need to change it to custom perfect gas. So now if you go inside custom perfect gas.h, you see that everywhere we have instances of perfect gas. You see like in the class and everything, it's just perfect gas everywhere. We need to change these stuff. So I'm going to say grep -rl. I'm looking for instances of perfect gas, and what I'm going to do over those files, I want to use a set with -i to in place, and I want to replace instances of perfect gas with custom perfect gas, and I want to do it globally. So now if you take a look at .h, you see that everywhere now we have custom perfect gas, perfectly fine. Now, congratulations, we have written our own equation of state. This video is over. But no, it's not as that simple, because you see that we have some source files in here, but we haven't compiled this equation of state, right? And we actually don't know yet how to compile it. So let's just go back to the source. Physical, no, but before going to the source, we have our equation of state in our hand, right? The new one. So now we need sort of a test case. So let's provide a test case for that. So we're going to tutorials. Let's go to the most, I said in the beginning that we want to basically do it for the most simple case, or the simplest case. And if you get the general idea, you can extend this. So let's go to compressible, and let's go to, I don't know, row pimple foam. And let's go to laminar, sine wave. Let's take a look at in constant. So first of all, once you're dealing with compressible solvers, you don't have a transport properties dictionary. Instead, you have a thermophysical properties dictionary. Well, on contrary, when you are working with incompressible solvers, you're always having this transport properties dictionary, which is far more simpler. But let's take a look at the content of thermophysical properties. You see that we have like bunch of stuff written here. We have the type as HESI thermo, mixture as pure mixture, transport as Sutherland, and thermo as H-const, and other stuff. So when in the beginning of this video, when I said that writing your own equation of state is not that straightforward, one sign is right here. You see that equation of state is just one piece of puzzle in the whole spectrum of other information that we are basically feeding in this dictionary. So now, at least you have one brief idea that what I meant by that in the beginning of the video. Anyways, I am going to, this test case looks perfectly fine to me. I'm going to copy that and put it in my EOS, and in my test case, copy -r that in here and sign. And let's go to system control dict. Let's go to end time is 0.02 with delta t of 2e minus 6. It's a lot of time steps. Let's make it 1, 2, 3, 4, 5. 5 is good. 10 time steps. And let's make this as time step, and let's write the results every time step. ASCII is fine, and adjust time step no, and rest is fine. So the first thing is that to make sure that the tutorial case that you have basically works out of the box without you changing anything or adding anything to the code. So let's just do an all run. Now, we have 10 time steps written, and let's take a look at OpenFOAM. You see that it selects the thermodynamics package. If I can scroll down, again, the same parameters, and then you see that the simulation went down perfectly, and we hit the end here, right? So now let's say if I, for any reason, I make a mistake here, like I HE thermo. Instead of that, I put a, I don't know, a strange name in there. Now let's try to clean this and to run this again. Take a look at this log OpenFOAM. You see that it says fatal error, and then it says fluid thermo, only the valid types are 214, and you see these are all the 214 valid types that you have at your disposal. So there are things that you can already notice in there. You see that these types are hugely nested templates, right? So again, it shows the complexity or not being straightforward when we are talking about writing your own equation of state is not that straightforward. The reason is that it's basically one piece of the puzzle. There's a lot of other information that you need to basically put in together so that you basically can use that certain thermal package in your simulation. The other point that you can notice is that once you're working with these templates and nested templates and everything, then there has to be somewhere that we instantiate those specific types. That's very important. That's the key that later we are going to figure out that where the heck those equations of states are getting compiled. So there has to be a point that we are instantiating those specific types for the template parameters that we are basically sending, right? Okay, anyways, but remember these 214. There are only 214 sort of possibilities in here, and you can also take a look at the a nicer look in a table, which basically gives you type, mixture, transport, thermal, equation of state, and so on and so forth, right? Okay, so I am going to go back. Now that we know that we are using OpenFOAM, let's also jump to the solver itself, because we said this is like the most simple case. So let's go to solver, compressible, and let's go to OpenFOAM. Let's go to make and options. Let's look for a thermophysical. You see that the thermophysical models we are using for OpenFOAM, it's only the basic thermal package. And what we are linking against is fluid thermophysical models, and we are linking also against a species. So let's copy that. I want to copy this name in here because we need to figure out, oops, if I can only type that Q hashbang. Sorry, QBang. Anyways, so now I'm going to jump into my source. I'm going to jump into my thermophysical models, and I'm going to grab for that name. That without the L, of course, the fluid thermophysical models. Now you see that actually we don't need the L because we want to see what is written in there. So you see that solid thermo uses the fluid thermophysical models, but it doesn't define it. There's only one instance in all these occurrences, and that is inside basic. And this is where we define the fluid thermophysical models. And that directory should be of our interest because OpenFOAM is using that basic thermal packages. So I'm going to go inside. I'm going to show you in make and files. We are compiling a lot of .c files, a lot of source files, and then we are calling that, packaging it into fluid thermophysical models. Okay. So now going back to the question that where our equations of a state are basically getting compiled. So let's go back to species and equations of state. Let's go, I don't know, like Peng-Robinson gas. Copy that. And I am going to grab -RL Peng-Robinson gas. And I'm going to hit the return key. You see that other than the species, which these are the actual source code of the Peng-Robinson gas, it also occurs at basic. And as we said, like seconds ago, we said basic is probably something which is interesting to us because our solver OpenFOAM is using it as the basic thermo package. So let's just jump into that and grab that again. You see that it happens in SciThermo and in RowThermo. So let's take a tour first. You see that we have a basic thermo in here. So let's take a look at basic thermo.h. This is sort of the abstract base class for fluid and solid thermodynamic properties. And what we do next is that we're going to take a look at fluid thermo, which fluid thermo.h shows that we have, description says, fundamental fluid thermodynamic properties. And what we have here is that it extends basic thermo, and it also extends it based on compressible transport model, if that makes sense. In the beginning, we also said that once you're working with these thermophysical dictionaries and stuff, you're probably working with a compressible solver, hence you're working with compressible transport models, if that makes sense. And on top of that, those two other directories, SciThermo and RowThermo, let's take a look at them. For example, SciThermo, if I grab for that without the L, of course, you see that there are like multiple occurrences, and it happens in zone thermos and also in SciThermos. So let's just go to SciThermos .c. So where's Peng Robinson? First, we included up there. And then now it seems like we are using some function called make thermos, and we are passing a lot of information in that. And one of those, as I said, pieces of the puzzle is the equation of state. Remember once I was talking about those nested template parameters? Then I said like we have to somewhere instantiate them. So it feels like we are instantiating those template parameters more specifically with this function make thermos, right? So probably this is how our equations of state are somehow getting compiled, but we don't know how this is happening behind the scenes, right? So let's just copy make thermos. And let's go back and take a look at grep minus RL that make thermos. You see that it happens in SciThermo and RowThermo. So we have two classes of thermo packages. One is based on compressibility and the other one based on density. But other than that, it also happens in fluid thermo. So let's take a look at fluid thermo, and let's take a look at make thermo. That's where it happens. So there we go. If you search for make thermos, you see that we have a hash and then define. Macros. If you don't know what they are, please go back to learning by doing C++. I made a video about macros. And in this case, it acts like a function. It takes parameters. And it takes a lot of parameters. In this case, it takes base thermo, C thermo, mixture, transport type, thermo, equation of state, and species. And equation of state is just one piece of information. What it does with it, what it does is actually it uses another function. It seems like it because it takes parameters, and it passes in all the five last parameters in here, which are transport type, thermo, equation of state, and species, are basically passed around in this function type def thermophysics. So let's look for that function. It is up here. It's simply doing a type def. Those nested templates with those arguments that we are passing in, it's going to put them in here and concatenate them into a single very long name, which consists of transport, type, thermo, equation of state, and species. What else do we do with these make thermos? We're using another function, make thermophysics thermo. We pass in those three first parameters, the base thermo, C thermo, mixture. And on top of that, the last parameter is actually that concatenation of all those rest of five things that we had in there. So let's look for this make thermophysics or thermophysics thermos. Very complicated names. Anyways, so you see that it is defined right here. It takes all those four parameters, and what it does, it has this defined thermophysics thermo. So I'm going to look for that function. You see that that function is defined here. Again, it's another type def. and it concatenates C thermo and mixture and thermo-fizz. And that thermo-fizz is basically that very long name that we had with transport type thermo equation of state and species, right? So that's what is happening. And then what else is happening? Let's go back here. It was here, right? So we had this one, and then on top of that, we have three of these instances of at thermophysics thermo, and then we have basic thermo, and then this name, fluid thermo, and then this name, base thermo, and this name. So let's look for this function. If you look for this function, you see that it's defined right here. This macro function, what does it do? It has add to runtime selection table. Ta-da! So all the magic is happening with these macros. So first, what we do is we instantiate all those stuff. We put some type defs to make the names simpler, but they are very long names. And after that, we are basically, once we have created that specific instantiation of those specific types, what we do is that we add them to runtime selection table. And that is the mechanism that once, for example, you type something by mistake, you see that it dumps out all those 214 sort of possibilities that you have. So now we generally have an idea what things, how things are basically happening here. And this add to runtime selection table is part of this add to runtime selection table.h. You can look it up also in the source code. It's a bunch of other macros that basically provides you this capability. Anyways, so it seems like this is where the magic happens in the basics. So this is very useful. I'm going to take this. I'm going to put it in my, like aside, like side to side to this custom perfect gas, let's say. I can copy it right here. But we can't basically mess around with, I could also change the source code directly, but probably that's the last thing you want to do because you don't want to mess up your original OpenFOAM installation. That's why I take the basic thermo package and I copy it into my run directory and EOS and that source code. I put it inside here because I don't want to mess up my original OpenFOAM files. So let's take a look at the files. First and foremost, we want to make this a little bit shorter for simplicity, but that depends on the application that you basically are aiming at. So in our case, I kept this psi thermos, and the reason for that was simply because, let me go to my test case. It's simply because of this this thing here. We are working with psi thermo. And I want to also keep that side by side because we need to pick the conditions, or the other pieces of the puzzle should be also the same as this one because our tutorial case is like that. We want to make it like easy for ourselves. But one thing which is super important is to put user in here because you don't want to mess up the original libraries. And then I'm going to give it like, probably not custom fluid thermophysical models, but probably like something like, I don't know, like perfect gas thermo, something maybe like that. And should I copy that right now? Because we need to, after compilation of this, we need to add this to, maybe I can do it right now even. At the end of the day, once we compile this library, we need to add it to our solver, the OpenFOAM. So I'm going to say libs, and I'm going to add, of course, without the name lib in here. So I'm going to delete these 3 characters. So it should be custom perfect gas thermo. So I'm going to save this, but I'm going to bring up this because we need that config. So let's save this, and now let's go to psi thermo, and let's go to psi thermos. Okay. As we said, a bunch of them are enthalpy based and a bunch of them are internal energy based. What do we have in our tutorial file? We're having sensible enthalpy. So whatever which is written here, we can get rid of it. In our very simple case, we can get rid of all those. The other thing is that we are using, for example, Sutherland transport. We can look for Sutherland. And you see that we have this with Yana thermo. This is not the one that we want. We want H const. So I'm gonna skip through, And we have this H-cons thermo here, and we have also perfect gas. So this second one sounds perfect to me. So I'm going to get rid of this, and I'm going to get rid of all the rest of this stuff. The only thing that I want to have, the only thing that I want to instantiate here is custom perfect gas, if I can type it though. So this config is exactly the same as this config in here. And the reason we selected it that way is because to make our lives easier, because this tutorial case is using that. So now I put here custom perfect gas, but do I have access to that header file? No. So I need to add it. Just like here, I'm going to add custom perfect gas. But I put custom perfect gas in there, but in making files, in making options, you see that we don't have access to that directory. So if I, for example, say vclean and vmake, it's not going to work because it's going to complain that custom perfect gas, I don't know where that header file is. But we already know that where that header file is. It's just actually here, right? It's in next to us, custom perfect gas right there. So what I'm going to do is to make an options. I'm going to copy this. Whoops. I'm going to say in foam run in EOS, and where was it? In source code, I think. And it was in custom perfect gas. So there we go. Now our solver, not our solver, our library should know about that header file. So let's do a vclean and let's do a vmake. Okay, you see that it's compiled perfectly fine. Now, what if I go to my test case? And I already added this lib here, this custom perfect gas thermal, right? I can also validate that as well. If I say foam user libbin, you see that I do have this lib custom perfect gas thermo.dylib. So it is already present in there. So if I say all clean, and if I say all run, let's take a look at the results. First of all, did you remember the previous number here? It was 214, but now it's 215. And the reason for that is because that we added that single specific combo that we wanted with our custom sort of equation of state. So let's look for custom. You see that custom perfect gas is also listed in here. And if you hit the next key, then you see that it's also written in this table as well. So now we successfully added it also into the runtime selection table, right? So now let's just not mess around and go back, and for the type, let's create this as HE thermo, and I want to use custom perfect gas to see whether it works. Let's do an all clean and all run, and now you see that it should basically run, right? You see that the simulation is perfectly fine. And if I search for custom, oh my God. If I search for custom, you see that custom perfect gas is selected as the thermodynamic package, as the equation of a state, right? But still, so the whole purpose of video was basically showing you this, but still it might be a little bit vague for you, so that you say, wait, but I still don't know where that compilation step happens. We saw all those macros, we went through them, how the type diffs works, and so on and so forth. But let's just go a little bit deeper, maybe. In basic, if I say vclean and vmake, you see that this is how thermos is basically getting compiled, right? I'm going to copy that. And since it's thermos.c, I'm going to go inside this directory, and I'm going to say, I am going to not create an object file out of that. What I'm going to do is to put it on something like log.c, and I want to, since we are in this directory, we don't need to say thermo in the beginning. Yeah, can I use a minus E here, capital E, because I'm interested in the step where the preprocessor basically works out all the source files and it dumps out the output of the preprocessor. So if I hit the return key, you see that it complains that it doesn't know where fluid thermal is. So we need to actually help him. I'm going to add this as, I think it's right here. I'm going to copy that. Source code and then basic and then ln include, which basically holds sort of symbolic links of all those header files. So if I hit the return key right now, you see that something is generated. This log.c is generated. So now let's take a look at this. If I search for custom perfect gas, you see that this is how the class was defined, right? So now you see that the compilation is actually happening here after the preprocessor basically does everything. So now I do have access to that custom perfect gas. And here's the step where the compilation happens. So if you want to like take a look at it, you can also go back and, for example, we can make a mistake in our custom perfect gas. Like let's go to our inline function implementation. And since this is like a psi based, I'm going to go to psi and make a mistake in here. I'm going to remove a parentheses in there. And I'm going to go back into my basic and I'm going to say vclean and vmake. Let's see whether it basically finds out this. And now you see that it actually figures out in the compilation of scithermos.c, after all those macros are basically expanded, it does have access to that custom perfect gas or the equation of state that you want to write for that matter. And if you make any syntax errors, then it's going to basically tell you that what is wrong with that. And also we can maybe, for the last thing that I want to show, we can also make like a fun experiment in here. Let's go into psi again. And I want to correct this mistake that I made, but let's just put an info statement here and say, I don't know, hello world, and put an end line in here. And I'm going to basically go back to, to my basic and vclean and vmake. And I'm going to my test case and I'm going to say all clean and I'm going to say all run to see what we get in here. Ta-da. Now you see that at every sort of time step, a gajillion times this function is basically being called. You see that all those hello world being printed everywhere. Like you see how many times this function is being called. Now you sort of understand where actually that compilation step of your equations of a state is basically happening. I hope that it was a very long video. I'm sorry for that, but I hope that you learned something from this video, and I hope to see you in the next one.